All right. Yeah, so this is a big project. The main collaborators for this work are Maureen Denol, who's an assistant professor here at UW also, Wes Thelen at CVO, and also grad students, Manuela Copley, Kash Garita, and Veronica Gaetel-Gata. Next slide, please. So the work that we're doing at Mount Rainier utilizes the global network of telecommunications optical fibers. Could you go forward? Sorry, I've got a bunch of built-in animations. This is going to be kind of painful because I'm used to just doing them as I talk. Go forward. So basically, we can use these fibers as a sensing network. Normally, next slide, please. Normally, we think about optical fibers for communication purposes. So this is a little picture from our lab of just a standard telecom optical fiber. You know, everyone's watching this on the internet right now. So, you know, the information is basically going from, you know, my computer, my screenshot, for example, is going from my computer. It leaves, it goes upstairs in my building to a server room where it gets converted from an electrical signal that goes like your networking Cat5 or Cat6 cables, and it gets turned with an optical transducer into an optical signal where, you know, goes through some telecom infrastructure and eventually gets decoded with another transponder and then turned back into an electrical signal. So that, you know, the basic idea is that the photons get from point A to point B. Next slide, please. But it turns out that not all of the photons get transmitted down the optical fiber. Some of them get reflected back. And so our sensing premise is that we can use those reflected photons. These aren't the ones that get used for communication. They're ones that get reflected back in the fiber. And we can use those reflected photons to do all sorts of stuff. We can measure things like their amplitude, frequency shift, or just the frequency. We can measure their state of polarization, and we can measure their phase. These are basically the four properties of electromagnetic wave. And we can use these different properties to estimate things like the simple one is we can take the temperature of the cable. So that's kind of easy to understand. I can tell you with sort of 1 meter scale sensitivity what the temperature of the cable is. I guess I should say 1 meter spatial resolution. For temperature, we do about 15 minutes in time. So we do about 15-minute time spacing. And in temperature accuracy, we can do about 10 millikelvin. So that's 1/100th of a degree centigrade. But actually, most of what I'm going to talk about today is not about temperature, although there is some temperature signals in our data. I'm mostly going to talk about distributed acoustic sensing. So it turns out we not only can we take the temperature of the cable, but we can actually measure the strain in the cable, how stretched out it is, at really, really high rates, at rates fast enough that we can actually measure passing seismic and acoustic waves. So I'll call this, technology is called distributed acoustic sensing, or just DAS for short. Next slide, please. So there is an optical fiber cable. I've heard a lot of folklore about this cable that I won't repeat because I'm not sure if it's true or not. But it goes from Ashford, Washington up to Paradise. So here's the setting. It basically follows, you know, the road from Ashford to Paradise. So a lot of it follows along the Nisqually River. If you go up one slide, forward one slide, please. So there you see starting in Ashford, it goes through the entrance station, crosses Couts Creek, and then goes up just following the road. So it goes by Longmire, eventually gets onto more intact substrate, takes the windy road, crosses the Nisqually Bridge, and ends actually in the visitor center. The end point of the fiber is at the visitor center. This is the optical fiber cable that that lets you have cell phone service when you're up at Paradise. Next slide, please. So just to give you a quick example of kind of what this data looks like, I'm going to start out by making an analogy with the seismic network, because data are broadly comparable to what you would get from a seismic network. So here is a magnitude 3 earthquake. It happened 20 kilometers south and east of the summit of Mount Rainier last week. It was actually a pretty good sized earthquake for Mount Rainier. There aren't that many magnitude 3s, kind of a handful a year. And so, you know, what you see here are records from 2 different stations showing the vertical and a horizontal component. That look like OPCH and PANH are the names of the stations. And you see P and S waves. So there's different phase arrivals on those blue squiggly lines or navy squiggly lines. That's just the P and S wave, right? So waves in a solid, it's not like sound waves. Sound waves, there's just one kind of sound wave. Waves in a solid that go through the interior of the medium are this through the body of the material. We call them body waves. There's two of them. There's a P and an S wave. So there's also shearing waves that don't exist in the air. And so this is, pretty standard seismic data. This is kind of, bread and butter seismology. Next slide, please. And next again. So this is all of, or at least a big section of the Pacific Northwest Seismic Network that recorded this event, just showing you that this was recorded on lots and lots of stations. And can you hit next, I think, twice? Yeah, there we go. So I'm just turning it sideways. That's all I'm showing you now. And so what we're going to do now is rather than thinking about these as wiggles, because you can kind of see this almost has an image-like quality when we're looking at so many of these together, is in the next slide, we'll switch to the view provided by Distributed Acoustic Sensing. So the orientation is the same here. Now, the horizontal axis is distance along the fiber, or what we call optical distance. So it's the distance that we infer by travel time of a pulse of light. We know exactly how fast light travels in optical fiber silica. And so we can figure out how far away we are on the cable. And then the vertical axis here is showing 1 minute. Same earthquake, it's that magnitude 3 that was 20 kilometers from the summit of Rainier. And we see those P and S waves, so that's good. The big take home right away is that we can use this technology for seismology. So we can do basic earthquake seismology, we can do detection and location, we can do seismic imaging and tomography using this data. We also see a bunch of other funny stuff that's kind of fun to comment on and think about. So if you could hit next, I think a couple of times, maybe 4 times total. So we have the PNS waves. We also have these bridge resonances. One more, please. We have evidence of some kind of variable coupling because we have big changes in the seismic amplitude over single channels, and we're not sure yet if that's because the cable is coupled into the earth differently in different places. Like maybe in some places it's in a conduit, and maybe in other places it's just directly buried into the earth. We also see these bridge resonances. So it turns out the cable goes over the Nisqually Bridge, and the Nisqually Bridge resonates a lot. It's constantly vibrating, and you can actually see it resonates more when cars drive over it. And finally, we have a big chunk of the cable that's in overhead lines, that we would call power lines or telephone lines or something like that. And that part isn't really useful for seismology in the obvious way. It turns out we do see PNS waves in it, which is kind of remarkable, but they're really distorted because they basically have to do with the vibrations of the telephone poles that are holding up the overhead lines. Next slide, please. So let's look at a few of these things. The first thing that I'm really fascinated by in these data are that it appears that this segment that goes from about 8 kilometers optical distance to about 16 there's elevated ground motion in this section, and this is exactly the part that's in the gorge of the Nisqually River. It starts right optical distance that's about 8 kilometers. That's right at the turnoff for Ricksecker Point. And the one at 16 is right near the Cougar Rock campground. And so, this region is, there's like really strong topographic effects, right? Like over a 1 kilometer, or I forget exactly what it is. I think it's over a 2 kilometer width of the gorge. The vertical elevation is almost a kilometer vertical, several hundred meters vertical. And so I think what this is some form of topographic amplification, although it's not working in exactly the way that topographic amplification is usually thought of. So I can provide some more details there if you're interested. But this is still something that we're working on figuring out, is why exactly the amplitudes are so variable over such short distances in the data. Next slide, please. Here's an example of the Nisqually Bridge vibrating. The Nisqually Bridge is actually the feature at about 12 kilometers here. So you can see it gets excited by the earthquake and then shakes a lot. So what I'm showing here is actually frequency. The black and white picture here is frequency on the vertical axis. Sorry for the small labels. And the horizontal axis is 50 days worth of data. And so those horizontal bands that stand out are those are the resonance frequencies of the bridge. So you see there's one at about 4 hertz, one at about 6 hertz, and then some higher stuff up at around 12 to 15. And then the vertical striping, where it goes from black to white, that's because the bridge mostly only resonates during the day, because it mostly resonates when cars hit it. And so we haven't done any detailed processing here. This is literally just a Fourier transform of the data. And I think you could probably extract it at night, but it doesn't, I don't have any reason to think it would change too much. What we still need to do is look at the full record that we have to see if it changes seasonally when the bridge has a bunch of time to cool off. Next slide, please. So that's what I've got for now. I'll leave you with the juxtaposing images of the beautiful surrounding environment of the Jackson Visitor Center with wildflowers. We installed the equipment in August, and a picture of the basement of the Visitor Center where our less lovely looking black box interrogator is installed. So thank you very much. Happy to take questions.
Alrighty, thank you, Brad. Very, very good presentation. Any questions? I don't see any comments right now. Any questions from the group? I guess I have one real quick. It's probably too far down in the network. Were you able to see anything from the August debris flow this year?
We started recording the week after.
Oh, that's right. Yep.
Yeah.
So no,
yeah, we just missed it. But I would say that the entire lower half of the cable is really in tune with the river. So for solid Earth stuff, for solid Earth seismology, it's actually a little bit of a problem to see the earthquake sometimes, because we see all sorts of noise coming out of the river, and I think it could be really interesting actually for folks interested in seismic noise generation from rivers.
Okay, there's a question here. Is the perfect storm possible for the Nisqually Bridge to end up like the old Tacoma Narrows Bridge, Galloping Gertie?
Well, I'm not a civil engineer, so I can't authoritatively answer that. However, you know, the bridge right now is really high off the ground. So I think if you know, the old one, my understanding is it was like just a few meters above the water surface. It was a much lower bridge. And so I think if the current Nisqually Bridge gets taken out by a lahar, then we've got much bigger things to worry about.
For sure. For sure. Marine added, we record all PNSN detected debris avalanches, though. Lots more to come.
Yep, I didn't include those, but there's lots of beautiful smaller avalanches, rock falls, what we think are small debris flows high up on the mountain. So not the big one that happened in August, but lots of the smaller ones, dozens and dozens, maybe even hundreds of them.
Interesting. Yeah, I'm curious if you also saw that avalanche near Mildred Falls the USGS talked about in their infrasound data, but we can talk about that offline as well.